So an MPI process usually, an MPI program is the same program that runs in different nodes, maybe in the same physical computer or in different computers. And it's usually the same code that in which the code flow changes with the rank. So the rank decides which parts of the code should be executed. So the main use case for MPI is the HPC clusters. This kind of facilities usually have a low latency network and a very high throughput network. So the nodes are all connected together using a local network. And here we can see, so the challenge is that we may have if we want to use this kind of technology, such as MPI, in a fog or edge computing environment. We have to identify three challenges. The first challenge is that we may have heterogeneous topologies. So instead of just running on a cluster, we have different nodes in different physical locations, so the latency between them may be different depending on which pair of nodes we are using. Then the second challenge is that the processors might not have the same computing power. And then the third one is that some of the devices may disconnect and connect, and this is not handled by MPI implementations. So the driving question of this work is that is it possible to bring both worlds closer so that the HPC community can take advantage of these resources? So can we use MPI in an IoT scenario? So in this work, we'll be dealing with heterogeneous topologies and also with different processing power of nodes. So let's see an example here of one of the collective operations that MPI implements, which is a broadcast. Broadcast is just a single process sending data to the rest of the processes. And there are many different ways in which the MPI library can handle this kind of operation. So here we have two different algorithms, a linear broadcast algorithm and a binomial tree algorithm. In the case of the linear broadcast, we have a node 0, which is usually it's called the root node. So it's the node that will be doing the send. And node 0 sends a message to node 1. I think we can't see very well the colors, but they will appear. So node 0 sends a message to node 1, and then it sends a message to node 2, and then to node 3, and so on, until the message has reached all the nodes. So these messages may happen overlapped in time. So when node 0 sends a message to node 1, and then sends a message to node 2, maybe node 1 doesn't have the message yet. So it's very difficult to see which messages are overlapped in the network at some point in time. And in the case of the binomial tree, which is the other algorithm, I think with the colors we won't get to see much, but node 0 sends a message to node 1, and then node 1 can also forward it to the rest of the nodes. So this removes the burden on node 0. So the node 0 doesn't have to do the work all by itself. So node 0 will send a message to node 1, and then in the next step, node 1 will send a message to node 3, and at the same time, node 0 can send a message to node 2. So that's also difficult to see how the messages go through the network at some point in time. And these algorithms are chosen from the different implementations that MPI libraries have, depending on the message size and the number of destinations. So the main assumption here is that the communication cost is the same for every link, so that we can rearrange the sends, and it doesn't take much more time to send a message from node 0 to node 2 than to send a message from node 1 to node 5, for example. And as we can imagine, in the case of IoT, since we have devices that are deployed all over the place, it's not always the case.